We saw in the previous example that when you have a series system of two components and each of those components has the exponential time to failure, then the system will also have an exponential time to failure, and the hazard function will be the sum of the hazard functions of the two components. So in this new example, we're going to look at placing those same two components in parallel, and the first component will again have a hazard function of 1, and the second component will have a hazard function of 2. And so the system will look like this. Two components placed in parallel. And if we, for the moment, assume that time is measured in hours, this first component is going to have an exponential distribution with a failure rate of 1 failure per hour, and the second component will have a failure rate of 2 components per hour. Well, what that means is this first component will be the stronger of the two components, and the second component will be the weaker of the two components. There are two things we'd like to find in this example. The first thing, we would like to find the hazard function of the time to system failure. And then the second thing we'd like to find is the mean time to system failure. So as usual, we began by looking at the survivor functions, and our first component has a hazard function that looks like this, and using the 5 by 5 matrix you can conclude that its survivor function is e to the minus t. The second component has this hazard function, and again using the 5 by 5 matrix you can show that the survivor function for the second component is e to the minus 2t. Now, for a two-component parallel system from the previous chapter, from chapter 2, you know that the reliability function is 1 minus the quantity 1 minus P1 times the quantity 1 minus P2. So all you need to do to get the system survivor function is you need to take and write the reliability function with P1 replaced by S1 of t and P2 replaced by S2 of t. Again, S1 of t is e to the minus t, S2 of t is e to the minus 2t. When you simplify that expression, you can see the 1's drop out, and you get e to the minus t plus e to the minus 2t minus e to the minus 3t. Now, one thing you recognize right away from that is that particular survivor function is not exponentially distributed. And the question is going to be, why is it not exponentially distributed? If component 1 is as good as new, and component 2 is as good as new, which is they both have the memoryless property, why isn't it the case that a working system is as good as a used system? Well, here is the reason. You might have component 1 functioning at some point in time, but component 2 has failed. Well, that's a system that is still operating, and is it as good as a new system? No, it's not, because a new system would have both of those components operating. So the reason that this is not exponential is a functioning used system is not necessarily as good as a brand new system. Now, if we return to the exponential example, in this case we had a two-component system, but the only way for that series system to be operating we had to have both of those components operating, and because they're as good as new, the system will be as good as new because they have to be operating for the system to operate. That's not true with the hazard function. We still that isn't true with the two-component parallel system. We still haven't gotten our first thing we need, which is the hazard function, in order to go from the system survivor function to the system hazard function. You again use the 5 by 5 matrix, and in that 5 by 5 matrix, the correct entry is minus s prime of t divided by s of t. So all you need to do is put your survivor function down here in the denominator and then take the opposite of its derivative. That gives you the numerator. And not surprisingly, this hazard function is not constant because the system does not possess the memoryless property. Finally, the last thing, we use a shortcut formula to find the time to system failure, and that is mu is the integral from 0 to infinity of s of t dt. Remember, this only works because this is a lifetime, so it is a positive random variable. So we take the integral of the survivor function, which is this, and leaving out the details, you wind up with 7/6 as your mean time to system failure. So here are a couple notes. The mean time to failure of that stronger component is 1. The mean time to failure of the weaker component is 1/2. The addition of the weaker component in parallel with the stronger component increases your mean time to failure by only 1/6. Our 7/6, which we have up here, is only 1/6 more than the mean time to failure of that stronger component. This is yet another illustration of the law of diminishing returns for parallel systems. You only get a little bit of help by adding that weaker component in parallel. Here is one last more complicated example. Let's say we have a 3-component system. They have independent exponential lifetimes, and in fact all 3 of the components have identical survivor functions. All of them are e to the minus lambda t, so those are exponentially distributed. So component 1 has failure rate lambda, component 2 has failure rate lambda, and component 3 has failure rate lambda. What we would like to do is find two things. The first is the system survivor function, and the second is the system hazard function. So for this particular system, we know from the previous chapter that the reliability function is that quantity, P1, which is the reliability of the first component, is in series with the parallel subsystem consisting of components 2 and 3. So P1 is going to get multiplied by the 1 minus P2, 1 minus P3 to give the reliability function. The next step is to take P1 and replace it with S1 of t, take P2, replace it with S2 of t, and P3 gets replaced with S3 of t, and that leads you to this quantity right here. When you multiply that out, you will see that the 1's again cancel, and then when you multiply by e to the minus lambda t, you wind up with this as a system survivor function. Once again, going to the 5 by 5 matrix, the hazard function can be written as the opposite of the survivor function, the derivative of the survivor function, divided by the survivor function. So here is the survivor function from just above, and when you take the opposite of the derivative of that, you get this quantity, and when you simplify, you wind up with this quantity. Now we're going to take a careful look at this hazard function, because we have actually answered the question at this point. We have given the system survivor function right here, and we have found the system hazard function right here. But we're going to take a look at what happens at t equals 0 and at other values of t to kind of get a feel for what's happening with this survivor function. So first of all, consider when t equals 0. When t is equal to 0, there is effectively only risk from component 1. And the reason for that is components in 2 and 3 are backing one another up. And so it won't be surprising that at t equals 0, the main risk comes from component 1. And so that's why this survivor function, this hazard function here is starting at lambda. Now, as time passes with this system, chances are one of components 2 and 3 is out if the system is still operating. So let's arbitrarily just say component 3 has failed and component 2 is now working. Well, if that's the case, now the system looks like a two-component series system. And if you remember, if each of these has failure rate lambda, we add those two lambdas together, and so in the limit, as t goes to infinity, this hazard function is going to approach 2 lambda. So that's an explanation for how the hazard function takes on this particular shape. So to recap here, as time passes, the system continues to function. It is increasing likely that either component 2 or component 3 has failed. So the system is approaching a two-component series system in the limit as t gets large, which has a failure rate which is the sum of the failure rates of the two surviving functions, two surviving components, and that means the limit as t goes to infinity of h of t is 2 lambda.